Hi everyone, welcome back. So today we will actually look at solving Maxwell's equations. So far we've introduced Maxwell's equations, we discussed material properties, and we looked at some tools and theorems. But today we are actually going to get into the meat of the matter, which is solving Maxwell's equations. So let's do that. This is probably one of my favorite lectures in this course. So we are going to introduce electromagnetic potentials to solve Maxwell's equations. All right, so let's go back and revisit Maxwell's equations once. So this was what we did in the first lecture. Curl of H is dt over dt plus J. And we had divergence of D was rho, and curl of B was 0. Right, so this was the original Maxwell's equations without any magnetic charges and sources and currents. So we'll start from there. We'll treat the magnetic case separately. Okay. All right, so we know that these two are the homogeneous Maxwell's equations because they don't have any sources. Right, so we'll start from there. Okay, so you know that divergence of curl of some vector field is always 0. And since the divergence of B is also 0, we can write B as the curl of some vector A. Okay, and we'll call this vector field the magnetic vector potential. Okay, and then we can substitute this B into Faraday's law, and that gives us curl of E equal to, did I have a minus there? Yeah, minus d dt, the curl of A, right? And I can pull this curl to this side. I can put a plus sign here. See, this is equal to 0. Now I can take the curl outside and the derivative with respect to time inside, and that gives me curl of E plus dA over dt equal to 0. And once again, I know that curl of gradient of some vector field phi is always 0. So I can write this as the gradient of some scalar field phi, right? Not vector field. And this phi is called the electric scalar potential. So if you've done electrostatics, that is your actual potential. The work done per unit charge in moving that charge from infinity to that position, right? And that's where you get the voltage, the definition of your voltage from. Okay, so based on this, we can write E as, so for the sake of convention, we actually put a negative sign here. And the reason that negative sign is there is that typically we want the electric field to go from higher potential to lower potential, right? Whereas the gradient points from lower potential to higher potential, and that's why there is a negative sign there. Okay, so with that negative sign, then you get E is minus gradient of phi minus dA over dt. Okay, so essentially we have defined E and B in terms of two potentials, the electric scalar potential and the magnetic vector potential. And since we're assuming this is a homogeneous medium, we can also write H equal to 1 over mu curl of A from the constitutive relations, and B equal to 1 over epsilon minus gradient of phi minus dA over dt. Okay, so next we make some space here. Okay, so these relations are the relationships between the fields. EB, H and D with the potentials, right? Just make the square again. Okay. So given these four equations, actually there's two clarifications I want to make before I go forward. So there was one kind of not very rigorous step that I made, two non-rigorous steps. So the first one is this one, and the second one is this one. Okay, so what I said here is the divergence of curl of A is 0, and we know the divergence of B is also 0, so B is equal to curl of A. But that's not obviously true, right? So you can take a simple example of derivative of 1 equal to derivative of 2 equal to 0. That doesn't mean that since they are equal, 1 equal to 2, right? So there is actually a theorem in vector calculus which tells you this, that if I have some vector field x and the divergence of this vector field is 0, then that is equivalent to saying that x can be written as the curl of some other vector field y. Okay, so there's a theorem that says that. That's what we're kind of implicitly using here. And similarly, if you have the case where you have a curl of a vector field x equal to 0, implies that x can be written as the gradient of some other scalar field psi. Applies and back actually. The reverse implication is trivial, right? Because we know curl of gradient is always 0 and we know divergence of curl is 0, but the forward implication is not that trivial. In one case, you have to use a construction to define what x is, and in the other case, you can use the fact that it's a conservative field, so it only depends on the endpoints, and then from that, you can pretty easily prove that the second relationship. Anyway, we don't have to do that here. It's not a mathematics class, but just know that there is a theorem which allows us to do this. Okay? All right. So given that, can you erase this stuff? Okay. So now that we know that we can write the fields in terms of these potentials, we want to know what equations the potentials have to satisfy. Right, so we know fields satisfy Maxwell's equations. So can we substitute these relationships into Maxwell's equations and find a certain set of equations that these potentials satisfy? Okay, so that will be our next goal. Okay. All right, so let's do that. So in order to do that, we want to find essentially the potentials as a function of the sources. And since we've already exhausted the homogeneous Maxwell's equations, we can go to the inhomogeneous part and try to derive those relationships. Okay, so from the inhomogeneous Maxwell's equations, this is the modified Ampere's law, which has the source J. And then I can substitute H and D from here and look at what A and phi satisfy. Okay, so substituting in A, I have H equal to curl of A divided by mu is equal to epsilon d dt of E. I know E is nothing but minus gradient of phi minus dA over dt plus J. Right? And I know that curl of A is nothing but the gradient of the divergence of A minus the vector Laplacian of A. And then I take the mu to the other side and I bring these terms to the left. That gives me gradient of d phi over dt plus mu epsilon d square A over dt is equal to mu j. Okay. All right. So we can again rearrange these terms a little bit. And what we get is the vector Laplacian of A minus mu epsilon d square A over dt square minus gradient of divergence of A plus mu epsilon dphi over dt is equal to minus mu j. Okay, so this is an equation that A and phi satisfy. Okay, and we want to see, can we simplify this, right? And luckily for us, there is actually a very elegant way to simplify this. So how do we do that? So the question is, have we uniquely defined A and phi? Okay, which means that given the fields, do we know what A and phi are? And the answer to that question actually is no. Right? We can see it pretty easily. So let's say I define B as curl of A. Right? So given E and B, can I get a unique version of A and phi? And the answer is no, because if I choose a different A prime, let's say, as A plus gradient of some arbitrary scalar function psi, right? And I choose a different phi prime as phi minus d psi over dt, right? Where we know that E was given by minus gradient of phi minus dA over dt, right? So this combination of A and phi gives me E and B, but we'll see now that even the combination A prime and phi prime gives the same E and B. Okay, how do you see that? So if I write B as curl of A prime, that's nothing but curl of A plus curl of gradient psi, and we know this is 0. Since curl of gradient is 0, okay? And then we have E, that is minus of the gradient of phi. In this case, we use phi prime, it's d psi over dt, minus d dt, A prime, which is A plus gradient of psi. And this is nothing but minus of gradient phi minus dA over dt plus ddt gradient of psi minus ddt gradient of psi. And of course, these two terms cancel out. So you get back the same equation again. Right? So we see that both A prime, phi prime, and A and phi, both these combinations give us the same E and B. Right? And that means that A and phi are not unique. Right? Okay, if A and phi are not unique, can we find some relationship between them? And what kind of relationship would you like to define? Can we define an arbitrary relationship? And the answer to that is also no. Right? And why is that? Because we know that B is given by the curl of A. Right? Which means that if the curl of A is defined, the only thing I can define now is the divergence of A. Right? Because we know from Helmholtz's theorem that for a given A, I only need to specify curl of A, and if I specify also the divergence of A, then A is fully defined. Okay, under some conditions of smoothness and continuousness and so on and so forth. But okay, for our purposes, if I give you the curl and divergence of any vector field, then A can be uniquely defined. Okay, and since the curl is already given, the only thing you can really specify is the divergence of A. So you can set the divergence of A to be pretty much anything. Okay, that's the kind of intuition. So what should we choose for the divergence of A? Right? If we go back here and look at what equation this is giving us, based on this long equation, there's a very obvious choice for the divergence of A, right? And that is equal to negative mu epsilon d phi over dt, right? So if I choose the divergence of A is minus mu epsilon d phi over dt, right? That's a great choice because then that big equation, one big term drops out, right? And this choice of A and phi, or the combination of A and phi, is called the Lorentz gauge condition. You don't have to choose this to be the divergence of A. You can also choose the divergence of A to be 0. That's also fine. And that gives you a different set of equations for A and phi. But at the end, you still get the same fields. Okay? So depending on which gauge you pick, you get a different equation for A and phi. For example, in the Lorentz gauge, you'll see A and phi satisfy wave equations. And whereas in the Coulomb gauge, A would actually satisfy slightly more complicated equation and phi would satisfy a Poisson equation. And that's a little bit simpler than the wave equation, but in certain problems, it makes sense to deal with waves rather than to deal with Poisson, because in Poisson equation, you can show actually that it's very easy to see that in Poisson equation, you don't get a causal system, right? Because any impulse, you get an immediate change in the potentials everywhere else. So in electrostatic problems or quasi-static problems, it makes sense to use the Coulomb gauge. But in propagation problems that we deal with in this class, Lorentz gauge is more relevant, right? Now, of course, just because the potentials are not causal doesn't mean the fields also are not causal. Like, the fields are still causal in any gauge, but we also would like the potentials to be causal because then it makes things a little bit simpler for us. Right? So we'd like everything to satisfy a wave equation. And that's why we are choosing Lorentz gauge here. Okay? All right, so under the Lorentz gauge, there are also other gauges like Kirchhoff gauge and so on and so forth. We're not going to get into all that. But it's just a way to show you that there is an additional constraint which we can impose on the potentials, which can simplify some of the equations. Okay, so under Lorentz gauge, we end up with minus mu epsilon d square A over dt square is equal to minus mu j. I'm trying to make a box, I guess. Sorry. Okay, so this is a vector wave equation. Wave equation. And I should say in Cartesian coordinates, it separates into three scalar wave equations. The scalar wave equations in x, y, and z. Okay, and the last part is to get an equation for phi, and for that we can use the last Maxwell's equations, right, which is Gauss's law for electricity. So I have the divergence of minus epsilon of, oh shoot, I think I made a mistake earlier. Yeah, this should be epsilon times that. Okay, but it doesn't affect anything else. All right, so minus epsilon of gradient of phi plus dA over dt equal to rho v, or rho, let's just say rho, right? Okay, and now we can substitute again the Lorentz gauge condition. And once you do that, you can show that this is nothing but, well, let's do one more step. d dt, the divergence of A equal to minus rho over epsilon. Right, and now you substitute Lorentz gauge condition, and that gives you the divergence of phi minus mu epsilon second time derivative of phi equal to minus rho over epsilon. Okay. All right. So now we see that both A and phi satisfy the wave equation. So essentially we've reduced Maxwell's equations from 4 different equations into just having to solve one wave equation. Right? So this is a scalar wave equation. So what's the general strategy? So strategy is given sources J and rho. From the sources, we solve wave equation to get A and phi. And then from A and phi, we get the fields E and H, or D and D as well. Okay, that's the general strategy. So we're still left with two things. We still want to know one thing. We want to know how to solve the wave equation, right? And that's what we'll do next. Okay, before we do that, I actually want to mention one more quick aside, which is that this transformation that we made from A prime to A plus gradient of phi, and then from phi prime to phi minus derivative of psi, right? This is called gauge invariance. Okay, which means that making this transformation, potentials can change, but fields don't change, right? It means the fields are invariant under this transformation. And there's a very beautiful theorem, right? It's a gauge invariance plus Noether's theorem. Noether was a mathematician who showed that given an invariance in a given system, you can derive from any invariance a corresponding conservation law. Okay? And in this case, the gauge invariance, you apply Noether's theorem to gauge invariance, you get conservation of charge. And that's a very beautiful result, that from something as abstract as gauge invariance, we get something as fundamental as conservation of charge. And the other conservation laws also come from some invariant property. Time translation invariance gives you conservation of energy. Conservation of momentum comes from spatial translation invariance, and spatial rotation invariance gives conservation of angular momentum. Right? These are the four conservation laws, and they come from these four invariant properties. So I'm not going to prove this here. You can look up the proof and see from how gauge invariance gives Noether's theorem. And many years ago when I was a grad student, kind of went through it and actually derived it myself. So it's a kind of a good practice to try and do that. But anyways, that's kind of a quick aside. So, sometimes you'll hear things like potentials are not real, they're just mathematical tools. And to some extent that is true. And we see that in this class is that they're not unique, which means that they cannot be physical, but you can actually challenge that in many ways. So one way to challenge that is to say that, okay, potentials are satisfying something as fundamental as gauge invariance because that's what gives us conservation of charge. So indeed, they may be very much physical and very much real, right? And you can get into philosophical debates of what is real, what is not real, but there are also other experiments which have shown that potentials can in fact be fundamental. And these gauge invariant properties or gauge properties play a big role in quantum electrodynamics as well, where potentials actually play a very central role. I'm not really an expert in that, but it's just kind of an interesting aside to say that potentials, okay, at least in this course, are mathematical tools, but it's also kind of nice to keep in mind that they can be more fundamental than just this, right? Okay, so that's a quick aside. So let's get back to what we were talking about. So before we move on to solving the wave equation, let's also look at something called the Hertz potential. Before we do Hertz potential, let's do another topic, which is a quick derivation. So we kind of ignored magnetic sources, which we introduced earlier in the class. So we can put that back in and use duality essentially to find what kind of wave equation do they satisfy. It's fairly quick because we already just derived it. We can just invoke duality to find that result. D equal to 0 and divergence of B equal to rho m. Right, so once again, we can say that D is given by curl of AM and H is given by minus this times this dAm over dt, right? And this should be phi m. And the equation they satisfy, which you can derive once again from scratch, or you can apply duality. Minus mu epsilon d square am over dt square equal to minus epsilon jm. And phi m satisfies a similar wave equation. Minus rho m over mu. Okay, where am is the electric vector potential. And phi m is the magnetic scalar potential. And since we consider these sources separately, electric and magnetic sources separately, you can use superposition to get a general form where you have both, right? So with superposition, E can be written as minus gradient of phi minus dA over dt minus 1 over epsilon curl of AM. So I'm including both sources here, which means that you should have all four potentials. And similarly, dt minus gradient of phi m. Okay. Okay. So now that we know how to find the potential, we know that given potentials, how to find the fields, you can write these fields in this form in terms of the potentials. All right, so next we can discuss a different kind of potential, which is called the Hertz vector potential. All right, so what's the idea here? So the idea here is that, okay, we had a scalar potential and a vector potential, but they satisfied a relationship, right, which was given by the Lorentz gauge. So then instead of defining two different potentials, can we embed that Lorentz gauge into just a single potential, right? And that's the idea. So you can find all the fields from just a single potential. Okay, so if we define A as mu epsilon d pi over dt and phi as minus the divergence of pi, where pi is the Hertz vector electric potential or the Hertz vector potential. Hertz electric vector potential. Okay. All right. So given this, we can make these substitutions for A and phi and the relationships for E and H, and that will give us what we want, which is that E equal to gradient of divergence of pi minus mu epsilon d squared pi over dt square, and H equal to epsilon times the curl of d pi over dt. And what equation do they satisfy? That we can derive from modified Ampere's law. So we have curl of H equal to epsilon dE over dt plus J. So I can substitute these values on the left and right hand side. So the left hand side becomes epsilon d dt of curl of pi. And the right hand side becomes epsilon d dt E, which is gradient of divergence of pi, right, from what we have up here. So I just substituted these two things. Minus mu epsilon d squared pi over dt squared plus j. Okay, I can combine these two terms into one term. And that gives me d dt curl of pi minus the gradient of divergence of pi plus mu epsilon d squared pi over dt squared equal to j over epsilon. Okay, and we know that this is nothing but minus the vector Laplacian of pi from a vector identity, which means that we have Laplacian of pi minus mu epsilon d squared pi over dt squared is equal to minus 1 over epsilon integral of j dt. And that's the equation that pi satisfies. So that's also a wave equation, of course. Excuse me. And similarly, you can also find a magnetic Hertz vector potential, which would satisfy a similar wave equation. Et squared equal to minus 1 over mu integral j and bt. Right? And then once you have this, then E and H can be given by. So you can use again superposition to write both of them together. That's what I'll do here. Pi minus mu epsilon d squared pi over dt squared minus mu curl of d pi m over dt, and H is given by a very similar equation. T squared plus epsilon curl of p pi over dt. Okay. All right. So that pretty much completes our development of the potentials, where we showed that, from Maxwell's equations, we can extract relationships between the fields and potentials, and then we can also use the inhomogeneous Maxwell's equations to find what kind of relationships do these potentials satisfy. And it turned out that, okay, all of them basically satisfy a wave equation, right? So that's what we'll try to solve next. So we want to solve this wave equation. So here we'll take a heuristic approach. Right? It's not a rigorous solution, although the answer is the same. Later in the class, we will actually take a much more rigorous approach to solving the wave equation without assuming any prior knowledge. Okay, so here we'll see that it's not exactly completely rigorous, but that's okay for this point. Later we'll see the actual rigorous derivation. But anyways, let's go forward. So we'll take the scalar wave equation, because we said that vector wave equation, at least in Cartesian coordinates, can be separated. So if you solve this, it's essentially like solving the other one as well. Okay, so we start with this. And now what I'll do, what's the strategy? So the strategy is that given a coordinate system, I know the wave equation is linear, right? Which means that if I solve it for a point charge at the origin, then I can solve it for any charge distribution, rho. Okay? So that's the strategy, and we'll see how that plays out. So I'll say rho of r is nothing but q times delta of r. Okay, where delta of r is, so what is delta of r? So delta of r is delta x, delta y, delta z in Cartesian coordinates, and it's 1 over rho, delta phi, delta z in cylindrical coordinates, 1 over r square sine theta, delta r, delta phi, delta theta in polar coordinates. But in the unit for delta of r vector is 1 over meter cubed, right? Because delta of x is nothing but 1 over meter, and delta y, delta z is 1 over meter. This is 1 over meter, this is 1 over meter, and this is 1 over meter. This is 1 over meter squared, this is 1 over meter. So it's all 1 over meter cubed. Now, of course, the reason behind that is that we want integral delta of x dx to be 1. Since dx is meters, delta of x has to be 1 over meter, right? So that's why you have only a charge q and you have rho of r. All right, so since the charge is at the center, at the origin, we can impose spherical symmetry on this problem, right? Which means that any potential that you get out of this should also be spherically symmetric, right? Because the entire problem has spherical symmetry, which means phi of r vector is only a function of phi of r, right? D phi over d theta is equal to d phi. I should actually use capital phi here, not to confuse it with the little phi. It's capital phi here and here as well. Little phi is an azimuthal angle, so I don't want to make that confusion. Should be 0. Okay. So what does that give us? That gives us that the Laplacian of phi in polar coordinates. And polar coordinates are the natural coordinates because of the spherical symmetry. 1 over r square ddr, r square d phi over dr. And that's from lecture 0. We saw that. You can look up the table and see that the Laplacian has this form in polar coordinates. Right, so we can substitute this into our wave equation and try to solve it. But an easier way is to make a change of variables. So I'll define psi of r as r phi of r. Okay. So if I do this, you can show pretty easily that Laplacian of phi would be equivalent to 1 over r d square psi over dr square. Okay. All right. It's pretty easy to see. You can substitute this into this, which is psi of r over r, to this, and then take the derivatives, and you'll see that you will get nothing but 1 over r d square psi over dr square. Okay, so now that we have that, we can substitute that in the wave equation. And that gives us d square psi over dr square minus mu epsilon d square psi over dt square is equal to minus q over epsilon r delta of r. Okay. All right. So now we know at r not equal to 0, the right hand side is 0 because of the delta function, right? Which means that d square psi over dr square minus mu epsilon d square psi over dt square equal to 0. Okay, and this is the free space wave equation, which is well known, right? So the free space wave equation has a solution of this form, where psi is equal to f of t minus r square root of mu epsilon. Okay, so any function which has an argument like this satisfies this equation. Okay, so another way to say that is that any function r comma t of this form, r t minus r square root of mu epsilon satisfies this equation. Why is that? It's pretty easy to see. You can take this as second derivative of f. So let's say, so this can be written as d square f over dz square times dz square over dr square, right? Where z is this p minus r square root of mu epsilon, right? So let's say this, so which means that this thing becomes f double prime times minus mu epsilon f double prime times minus mu epsilon. Right? And then if we take d square f over dt square or dt square, that's nothing but, actually this should be plus. It's nothing but minus mu epsilon f double prime again, and then you add them and then they get cancelled, right? So it's a fairly simple derivation. Space. So any function of this form satisfies this equation. Right? So what is this equation really saying? Right? This is saying that, if I'm at some time t0, so let's look at this as a function of space. So this is r, let's say, and this is my function psi. So at t0, I have some function that looks like this, let's say. So this is f of t0 comma r, right? Then if I take t0 to t0 minus or t0 plus r square root of mu epsilon, right? This function has to move in space. So this is nothing but 0 plus r square root of mu epsilon. And because you can substitute t0 plus r square root of mu epsilon into this, and you would get the same function back. Right? Because plus r square root of mu epsilon and minus r square root of mu epsilon would cancel, and then you get the same original function back. Right? It's just shifted in space. And that means that nothing but this function is moving as a function of time. Right? So it's kind of should we erase this part? And let's copy this. P. It's not letting me paste. Anyways, so this is moving from here to here as a function of time and space at speed up. So up is the speed of this wave. And that's what a wave means, right? A wave is nothing but something that changes in time and space. And in this case, it's propagating in some sense at the speed up. Right? And here up is 1 over square root of mu epsilon. Square root of mu epsilon. Okay. All right, so maybe you've seen the wave equation in different forms before. So if you've taken a microwave engineering class, it shows up as the telegrapher's equations in one dimension. But here we deal with the three-dimensional case. And in three-dimensional case, any function that is moving in space at this speed satisfies this equation. Okay, so the generalized form of the wave equation is something like this. At squared minus 1 over c squared d squared phi over, it should be r, or x squared over dt squared equal to 0. That means the wave is moving in the x direction at speed c. Okay. Okay, so any function can satisfy this homogeneous wave equation, but the wave equation we were given is not homogeneous, right? It has this thing on the right hand side, and actually it's this thing when we use psi, right? So we want to know what is this function f when we have a source psi, and here is where the heuristic part comes in. Okay, so implies that phi is nothing but f of t minus r square root of mu epsilon over r, right? So you want to know what is f. Again, here we sort of so we rely on Coulomb's law in quasi-statics to give us what is f. Okay, so we know that Coulomb's law is nothing but q of t over 4 pi epsilon r. And given a charge q, that's what the potential is. And here we have this term. Okay, although Coulomb's law is for quasi-statics and we're treating a general wave equation, we can kind of argue that they should be equal. And from that, we can say that f of t is nothing but q of t over 4 pi epsilon. But this is not very rigorous. You may not be very convinced with this and say, okay, you can't just invoke Coulomb's law. You have to derive it rigorously, and that's what we'll do later in the class. But for now, we just go with this. Okay, so given that, this is our final solution. Okay, so that's phi of t, r comma t. Okay, so this was for when we had a point charge at the origin. But what if you have an arbitrary point charge somewhere in space? So now that we have the origin case, it's fairly easy to treat the other case as well. Straight line, x, y, and z. Okay, so let's say I have a point charge somewhere here. And I can write this as r prime. So use prime coordinates to define a observation source point. And we want to look at, let's say, the field somewhere here at vector r. So what I can do is I can place use a different color maybe. Orange. I can place a imaginary coordinate system or a local coordinate system here. Right? And for this coordinate system, Q is at the origin. Right? So here Q is at the origin. So my R in this expression here is nothing but this distance. Right? The little r without the vector. So in terms of the original coordinate system, R is, so this vector, we'll call it, we can call it R2, I guess. Okay. So R2 vector is R minus R prime, right, from vector addition. Okay, which means that R out here in this new coordinate system is the modulus of that. Right, so given some R prime, I can find R for that R prime as R minus R prime in vectors. Okay, which means for the general case, when I have a source in some arbitrary location R prime, my scalar potential is of this form, Q of T minus mod of R minus R prime divided by UP, all divided by 4 pi epsilon modulus of R minus R prime. Okay, And since R prime now is arbitrary, if I want to find it for a general distribution of charges, which are which are placed arbitrarily in space, then I only have to integrate over R prime. Right? And since everything is linear, I can just integrate over R prime and get the full potential. So the total potential as a function of everything is no longer a source of R, is no longer dependent on R prime, right? Because R prime gets integrated out by epsilon volume integral of rho v R prime minus mod R minus R prime over UP divided by modulus of R minus R prime dr prime. So this looks like a hairy integral, but it's really not that complicated. You can see that. Do that again. Okay. So you can do the same thing in Cartesian coordinates with the different a's, right? The ax, ay, az, and you get three equations like that, and then you can add them back up to get the vector form of A, which is now the solution of the wave equation for the magnetic vector potential. That comes out to be 4 pi. So we add them back up. And now it's a function of the current density, T minus R minus R prime over UP divided by modulus of R minus R prime dr prime. Okay, this also deserves its own box. Okay, so actually some space here. dr. Okay. So these two equations are essentially the solutions to the wave equation for phi and A. So this completes our strategy, right? So given a current distribution J and a charge distribution rho, all we need to do is plug them into these equations, integrate over space. That gives us A and phi as a function of space and time. And then from A and phi, from A and phi as a function of space and time, we substitute them into the relations we had earlier to get E and H. Okay, and you can use duality to find the relationship between AM and phi m and JM and rho m as well. But this is sort of for a general case, sort of a complicated integral. We will actually simplify this in the next lecture. So what we'll do is we'll say that, okay, the time dependence here is not really that important. Why is that? Is that given any charge distribution and current distribution that's varying with time, I can break it down into a combination of arbitrary sines and cosines using Fourier transforms. And then all I need to do is that find the solution for just one sinusoid, apply this integral, and then go back and add the other sinusoids as well. Right? So we only have to really solve this since everything is linear, and that's a great advantage of working with Maxwell's equations is that everything is basically linear. Of course, the medium can be nonlinear, but in a homogeneous linear medium, all of these equations are linear. Right? So we can apply Fourier analysis to simplify this quite a bit. And that's what we'll do next is we'll do harmonic expansions and see in the case of harmonic functions how these equations get simplified. And that will actually give us a practical way to find radiation integrals given a certain charge and current distribution. Okay, so that's pretty much it for today. If you had any more questions, or if you have any questions, you can leave them in the comments below. If not, I'll see you in the next one. Thank you.